Hello dear friends, in this video lecture we will discuss the last part of module 5. In the last two video lectures we have already discussed the first 5 topics of module 5. In this video lecture we will discuss the last 2 topics, that is minimal polynomial and Jordan canonical form. Minimal polynomial. The minimal polynomial m of x of an n by n square matrix is the monic polynomial of least degree such that m of a equals 0. So, the minimal polynomial will be monic. Monic means the coefficient of the highest degree term is 1. It is of least degree such that m of a equal to 0. When we substitute a, the answer should be 0. The minimal polynomial will always be a factor of the characteristic polynomial. If we denote the characteristic polynomial by p of x and minimal polynomial by m of x is a factor of p of x. The zeros of both p of x and m of x are the same, but they may have different multiplicity. Means the powers of the factors may be different. By Cayley-Hamilton theorem, we know that every square matrix satisfies its own characteristic equation. That is, when we substitute A in the characteristic equation, the equation is satisfied. So, if there exists a polynomial of degree less than that of the characteristic polynomial, such that when we substitute a, the answer is 0, then that polynomial will be the minimal polynomial. If such a polynomial does not exist, the minimal polynomial is same as the characteristic polynomial. Now we will check an example. Consider A equals matrix first row 2 0 0, second row 1 2 minus 1, third row 1 3 minus 2. To find out the minimal polynomial, first we have to find out the characteristic polynomial. The characteristic equation is determinant a minus lambda I equals 0, which gives lambda cube minus 2 lambda square minus lambda plus 2 equals 0, and its roots are 2, 1 and minus 1. Since 2, 1 and minus 1 are the roots of lambda cube minus 2 lambda square minus lambda plus 2, it can be factorized as lambda minus 2 into lambda minus 1 into lambda plus 1. So the characteristic polynomial in terms of x can be written as p of x equals x minus 2 into x minus 1 into x plus 1. Now the zeros of minimal polynomial m of x and characteristic polynomial p of x are the same. That is, the factors x minus 2, x minus 1 and x plus 1 are the factors of m of x also, possibly with different multiplicity. But here all the factors are of multiplicity 1. So they must exist in m of x also. So in this case, m of x and p of x are the same. So minimal polynomial equals x minus 2 into x minus 1 into x plus 1. Another example, find the minimal polynomial of a equals first row minus 2 2 minus 3, second row 2 1 minus 6, third row minus 1 minus 2 0. As in the previous case, first we have to find out the characteristic polynomial p of x. For that, the characteristic equation is determinant a minus lambda I equals 0, which gives lambda cube plus lambda square minus 21 lambda minus 45 equals 0, whose roots are 5, minus 3, minus 3. So using these roots, we can factorize the characteristic polynomial lambda cube plus lambda square minus 21 lambda minus 45 as lambda minus 5 into lambda plus 3 into lambda plus 3 or lambda minus 5 into lambda plus 3 the whole square. Replacing lambda by x, the characteristic polynomial p of x equals x minus 5 into x plus 3 the whole square. Here, the factors of p of x are x minus 5 and x plus 3. Both these factors should be present in m of x also, maybe with different multiplicity. So, the two different possibilities for m of x are either x minus 5 into x plus 3 or x minus 5 into x plus 3 the whole square. If A satisfies x minus 5 into x plus 3 equals 0, then that will be the minimal polynomial. Otherwise, the characteristic polynomial itself will be the minimal polynomial. Now we will check the first one. In x minus 5 into x plus 3, if we replace x by a, we get a minus 5i into a plus 3i. Now we will check whether a minus 5i into a plus 3i equals 0 or not. If it is equal to 0, x minus 5 into x plus 3 is the minimal polynomial. If it is not equal to 0, the characteristic polynomial itself will be the minimal polynomial. Now, a minus 5i into a plus 3i equals, we get minus 7, 2 minus 3, 2 minus 4 minus 6, minus 1 minus 2 minus 5 into 1, 2 minus 3, 2, 4 minus 6, minus 1 minus 2, 3. On multiplication, we get the answer as 0. Therefore, the minimal polynomial is x minus 5 into x plus 3. Here, p of a is also equal to 0, but remember that the minimal polynomial is of least degree such that when we substitute a in that, the answer is 0. Another example, find the minimal polynomial of a equals matrix first row 6, 5, 2, second row 2, 0, minus 8, third row 5, 4, 0. The characteristic equation is lambda cube minus 6 lambda square plus 12 lambda minus 8 equals 0, whose roots are 2, 2, 2. So, using these roots, the characteristic polynomial can be factorized as lambda minus 2 the whole cube, and p of x can be written as x minus 2 the whole cube, simply replacing lambda by x. The only factor of p of x is x minus 2. So, the different possibilities for m of x are x minus 2 the whole square, x minus 2 the whole cube. First, we will check whether a minus 2i equals 0. Clearly, it is not equal 0. So, we will check whether a minus 2i the whole square equals 0. For that, find out a minus 2i the whole square, and clearly it is not equal to 0. Since a minus 2i and a minus 2i the whole square are not equal to 0, the only possibility is a minus 2i the whole cube is equal to 0, and hence here also the minimal polynomial is same as the characteristic polynomial. Our next topic is Jordan canonical form. To study Jordan canonical form, first we have to study what is a Jordan block. A Jordan block corresponding to an eigenvalue lambda, denoted by j and lambda, is an n by n matrix with lambda on the main diagonal and 1 on the diagonal above and zeros elsewhere. The Jordan blocks of different orders corresponding to an eigenvalue lambda are: the Jordan block of order 1 corresponding to lambda is matrix lambda. of order 2. It's a 2 by 2 matrix. The main diagonal elements will be lambda itself. The diagonal just above the main diagonal is 1 and all other elements zeros. Now of order 3, main diagonal elements are lambda. The diagonal elements just above the main diagonal are 1. All other elements are zeros. Of order 4, the main diagonal elements are lambda. The elements on the diagonal just above the main diagonal are 1. All other elements are zeros. The Jordan canonical form of an n by n matrix is again an n by n matrix in which the diagonal entries are Jordan blocks. In this shown matrix, J1, J2, J3, etc., Jk are Jordan blocks of different orders and all other elements are zeros. If the characteristic polynomial factorized completely, we can convert a given n by n matrix to its Jordan canonical form. Let us check an example. Suppose the characteristic polynomial of a matrix be lambda minus 5 the whole cube into lambda minus 6 the whole square, and the minimal polynomial be x minus 5 the whole square into x minus 6 the whole square. Here, the number of eigenvalues is 5, which is the degree of the characteristic polynomial. Hence, the order of the Jordan canonical form is also 5. The eigenvalues here are 5 repeated 3 times and 6 repeated 2 times. So the diagonal elements of the Jordan canonical form are 5, 5, 5, 6, 6. The minimal polynomial is given as x minus 5 the whole square into x minus 6 the whole square. This will determine the order of the largest Jordan block corresponding to each eigenvalue. Corresponding to the eigenvalue 5, the factor is x minus 5 and the power of x minus 5 in the minimal polynomial is 2. So, the largest Jordan block corresponding to the eigenvalue 5 is of order 2. Same way, corresponding to the eigenvalue 6, the factor is x minus 6 and the power of x minus 6 in the minimal polynomial is 2. Hence, the Jordan block means the largest Jordan block corresponding to 6 is also of order 2. To write a Jordan block of order 2, we need 2 diagonal elements. So corresponding to 5, the Jordan block is 5, 1, 0, 5. The remaining 1, 5 will be treated as a Jordan block of order 1. In the case of 6 also, to write a Jordan block of order 2, we need 2 6s and the corresponding Jordan block is 6, 1, 0, 6. The different Jordan blocks are marked in the matrix and all other elements will be 0 in that. So this is the Jordan canonical form of the given matrix. Now another example. Find the Jordan canonical form of A equals first row 2, 1, 0, second row minus 1, 0, 0, third row 0, 0, 2. To write the Jordan canonical form, we need the characteristic polynomial as well as the minimal polynomial. So characteristic equation is determinant A minus lambda equal to 0 and the characteristic polynomial is lambda cube minus 4 lambda square plus 5 lambda minus 2. The roots are 2, 1, 1. So the characteristic polynomial can be written as lambda minus 2 into lambda minus 1 the whole square. Possibilities for the minimal polynomial are x minus 2 into x minus 1 or x minus 2 into x minus 1 the whole square. First, we will check a minus 2i into a minus I equal to 0 or not. Clearly, it is not equal to 0. Hence, the minimal polynomial is x minus 2 into x minus 1 the whole square. Order of the Jordan canonical form is same as the order of the given matrix or same as the number of eigenvalues. So here the Jordan canonical form is also of order 3. The diagonal elements are the eigenvalues which are 2, 1 and 1. Corresponding to 2, the factor is x minus 2 and the power of x minus 2 in the minimal polynomial is 1. So, the largest Jordan block corresponding to the eigenvalue 2 is of order 1. It is matrix 2. Now, for the eigenvalue 1, the corresponding factor is x minus 1 and the power of x minus 1 in the minimal polynomial is 2. So, the largest Jordan block corresponding to 1 is of order 2. It is 1, 1, 0, 1. So, the Jordan canonical form is 2 is a Jordan block, 1, 1, 0, 1 is a Jordan block. They are marked there and all other elements are zeros. Thank you.